Good day, everyone. Today we start to understand how a Verilog code can be written in many ways. There are many styles of modeling or writing a Verilog code. We will see how they can be written. What does a basic Verilog code look like? To start with, it looks like this. You have the keyword module, and then you have the name of the module. This is an identifier, which means it is user defined. And then you have the terminal list. In this case, the module name is half adder. In the terminal list, it includes X, Y, some carry, and these are the module internals. The module always ends with an end module. The components of a Verilog module, you have a start, a body, and an end, of course. To start with the name of the module, then the list of quotes, like we just saw right now, X, Y, etc. Then the declarations to define whether X, Y are inputs or outputs, that is declaration. And then there are parameters, constants, variables, all these come under parameters. You may or may not have them. That's why it's termed as optional. In the body, you might describe wires, that means intermediate signals that you have and other variables. If you are using data flow statements, this is one way of modeling it. Always starts with a assign keyword. You might have data flow statements. The second one is gate level modeling. So you might have instantiation statements. And the third one is behavioral modeling. So you might have always an initial blocks. These are the identifying keywords or blocks that you have in each modeling style. This is data flow, this is gate level, and this is behavioral. You may have a mix of all these because it is difficult to write a long code or a complicated code using a single style alone. You have to mix it to get a proper efficient code. You may also have repetition of codes which will be unified as a single function or a task. And finally, the module ends with an end module statement. The basic building block is always a module. You start with the keyword module and you end with the keyword end module. You can always make modifications inside the module. That means inside the half adder, you can do it using different styles. You might use different logic. But ultimately, what you're doing is a half adder. That means sum is equal to a plus b, and whatever carry is generated will come out of the carry. So this up to the designer how to implement it, but the functionality has to remain the same. The internals of the module are hidden from the environment. So whatever changes you bring inside the module, as long as you don't change the functionality, you can just proceed without any change in the environment. The levels of modeling include behavioral, data flow, gate level, and switch level. Behavioral basically describes the behavior of the code or behavior of the module actually. This is actually using the truth table of your module. Data flow describes the flow of data inside the module. It is described using Verilog code, and that style of modeling is called data flow. Gate level describes the circuit in terms of gates. And switch level also describes the circuit but in terms of transistors, etc. That is a more core level. Okay. So these are the different levels of modeling that you can use in Verilog. Let me explain the different modeling styles a little detail using the AND gate example. I'll start with the gate level modeling. Okay, this one takes a little time to understand, so listen carefully. Here, the implementation is in terms of logic gates and the connection between the gates. Take an example here. I have module AND gate level ABC. Inputs A and B are declared. Output C is declared. All these are the usual rudimentary flow of formalities for the Verilog code. And then what you have here is a statement like this. This is referred to as the instantiation statement. Let me try to explain what instantiation statement does in reality. In the Verilog library, there are inbuilt functions, and one of those inbuilt functions is AND. You can use the AND code, the code for AND gate, from the library in our main code. How I do it is I inspect the AND gate that is already inbuilt. I need to know this. Okay, the AND gate has inputs X and Y and the output is Z. It is declared as module AND Z, X, Y. In my code, I need to bring in a gate, and that gate is AND gate. When I bring in that gate, what I do is I create a copy of this AND gate in my actual AND gate level, the code. So when I bring in that copy, I'm actually replicating it, creating a hardware copy of this original AND gate. Therefore, when I'm making a new hardware copy, I have to call it by a different name because these two are different. They are not the same hardware. They are different, even though it does the same thing. So I've created a copy. I'm calling it by a new name. The next thing I have to do is, since it performs the AND operation through X and Y and producing Z, I have to make the connections here. I want to do AND operation of A and B. So I connect A to X and B to Y. The Z produced I have to see on C. So I make the connection between Z and C. This entire process of replicating the already written code for AND gate, bringing it here, calling it by a new name A1 and making the connections. This is referred to as instantiation, and it is summarized in this single line of code. You see the word AND, it means that the code for AND is written somewhere else. And since it is in blue color, the reason is that it is an inbuilt function. It is an inbuilt module. That is why it is written as AND. Okay, it is predefined. And the one that you have created is called by the name A1. So you call it A1. I want to connect C to Z, X to Y, A, and Y to B. So I look at the first port here, it is Z. So I write C here because I want C to connect with Z. The second one should connect to X and the third one should connect to Y. This kind of a connection is referred to as ordered connection. I can do connection by order in which it is written. So the first one will automatically go to the first one of this module AND. The second one A will automatically go to the second one of AND, and so on. So the order matters in this case. I am not specifying whether Z is connected to C, but the order infers that Z is connected to C. In this manner, I can declare, instantiate the entire module, AND module. Okay. So this is how I do the gate level modeling for AND gate. Very simple case. Look at the simulation. I see that the inputs are 0, 0 here, the output is 0. Input 0, 1, output is 0. Input 1, 0, 0. Input 1 here, right here, and here, and the output is 1 again. Hence, the AND gate functionality is satisfied and verified. Now let us take the case of a half adder, where the sum is equal to A XOR B and the carry is equal to A and B. This is something we already know. Okay, I have to use gate level modeling for this. Let's start with the keyword module. As we all know, module. The name of the module is half adder, and the output ports are A, B, sum, carry. Inputs A and B are declared, output sum and carry are declared, and the expected gate level circuit looks like this because sum is equal to A XOR B and carry is equal to A and B. In order to replace the circuit that we just saw right now, what is it? Sum is equal to A XOR B. Right? So in order to do that, I bring in the XOR gate like we did for AND gate. XOR, the keyword is XOR. It is predefined. XOR, I call it by a new name U1 and I make the connections of output sum, comma A, comma B. And AND gate is brought in because I need to do carry. Carry is equal to AB. So U2 is the name that I give to the module that I've copied to my module, that is half adder. So I've brought a copy of AND gate into half adder. I call it by the name U2 and I make the connections carry A, B to carry A, B. Okay. So this is all I have to do for a half adder. Suppose I have to make a full adder using a half adder. I mentioned that we are using predefined gates like AND, XOR, etc. And that time you were using the words XOR and so on. Suppose you have already written a module, like here in the case of half adder. I want to use this half adder inside another Verilog code. I can do that. That is also gate level modeling. You are bringing in an entire module, half adder module, into the full adder. That is my question. Full adder using half adder. I've already got the circuit out here. We are more interested in the code right now. So I look at the circuit. I have a half adder here. The inputs are A and B. Outputs are produced here. I have another half adder here and an OR gate here. You see that there are wires also used here. That is interconnections. Let me call these wires by these names. The first sum output, intermediate sum output here is sum1. The first carry output here is carry1. The carry output in the second half adder is carry2. These are the names I'm giving the wires of the intermediate or the intermediate wires. Okay. So when I start the module, I call it by a new name, full adder. I declare the outputs and inputs like I do usually. Wire sum1 carry1 carry2, as we have mentioned here, is also declared in particular. Now I'm going to use a half adder that I've already written here. I have to use the instantiation statement. We start with the name of the module. What is the name of the module? Half adder. So write half adder. This is the half adder. Okay. Half adder. HA1 is the name of the copy that I have created here. This is a HA1. Okay. And what are the ports? In which order? Sum, carry, A, B. In this case, what is the sum here? The sum is called sum1, comma. Okay. So I've written sum1. What should I write here? For carry output, carry1. So I've written carry1 here. What are the inputs to the HA1? A, B. No issues. A, B. Okay. So the first half adder I've instantiated. The names are sum1, carry1, A, B. In the order in which I have written it in the original half adder module. Take care. In the order in which I have written it in the original half adder module. Sum, carry, A, B. Let's look at the second instantiation. I need to use one more half adder. That means I have to create one more copy. This copy I'm going to call it as HA2. The same half adder here. I call it HA2. Okay. In the same order, sum, carry, A, B, I have to show the connections. So this half adder, the connection. This output is sum itself, because you see output is final output. This is the final output. This is sum. Final output sum to sum. Then carry is carry2. So I write carry2. AB. Instead of AB, I get sum1, comma, carry in. Correct? So I write sum1. And what is the carry in? CN. CN. Okay. And finally, I have one more thing, that is the OR gate. The inputs to the OR gate are carry1, carry2, and the output should be carry. So I got output carry, comma, carry2, comma, carry1. Okay. It doesn't matter which order carry1 and carry2 come, because it is an OR gate. And that's all. So you have already brought in the new modules, you made the connections appropriately, and if the circuit is correct, this code should work and give you the correct output of a full adder. That's all. You remember how I mentioned that the ports of the main module is connected to the terminals of the instantiation list? The method that we followed was ordered list, because you see, I said sum, carry, input A, B. This order should be followed when I instantiate the same thing. Sum1, carry1, A, B. That order should be followed. That method was actually referred to as connection by ordered list. That is the first method of connection. The second method is connecting by name. Suppose for very large modules you have 50 ports or something. You cannot remember the order in which the module has defined it, and you might make a lot of mistakes. So what you do is, you write something like this, that is, instantiate the module and then you write the original and the module names. This is the name of the original module, this is the name of your top module. Top module meaning the code that you are writing right now. This is the one that you are calling in. Okay. So when you put one dot cout and the other one in bracket cout, we are connecting small cout with capital Cout. Both of them are two different things. When you do this, you are connecting sum with capital sum. Okay. If you have any port that you don't want to connect at all, just simply leave it out. You don't have to worry about it. So yeah, I hope that is clear. In this way, you can do any gate level modeling by instantiation statements. I hope that is clear to you guys. Okay. Look up more problems, please. More programs. Try to implement it. Do well. Thank you.